On September 3, 2025, in the frozen, windswept waters of the Norwegian Sea, something happened that will be studied in military academies for decades. A single B-2 Spirit stealth bomber, one of the most sophisticated aircraft ever built, released a weapon that military analysts are already calling one of the most consequential developments in maritime warfare since the invention of the guided missile. The target, a decommissioned vessel anchored in the icy waters near Andøya Island, Norway. The result, complete and total destruction. The location, just 366 miles from the Russian border. This was not a routine test. This was a declaration. What the B-2 dropped that day was not a conventional bomb, nor an expensive, complex anti-ship missile. It was something far more clever, a system called Quick Sync, developed by the Air Force Research Laboratory, and it represents the kind of asymmetric ingenuity that has defined American military superiority for generations. To understand why this matters so deeply, we need to start with the problem it was designed to solve. The problem with conventional anti-ship warfare. For decades, the dominant thinking in anti-ship warfare revolved around dedicated, purpose-built missiles. Weapons like the AGM-84 Harpoon, America's long-serving anti-ship missile, or the more modern long-range anti-ship missile, known as LRASM, are extraordinarily effective. The Harpoon, which entered service in 1977, can strike surface vessels at ranges exceeding 80 miles, flying low over the water to evade radar. The LRASM takes that concept much further, incorporating autonomous target recognition, low observable flight profiles, and the ability to navigate around known threats before selecting its own impact point. But these weapons come at a steep price. A single LRASM costs approximately $3 million. Even the older Harpoon runs into the hundreds of thousands of dollars per unit. In a high-intensity naval conflict, the kind of fight that military planners are increasingly concerned about in the Pacific or North Atlantic, a fleet could exhaust its stockpiles at an alarming rate. During the Falklands War in 1982, the British Navy fired through its anti-ship missile inventory faster than anyone had anticipated. Modern conflicts, with faster ships, denser engagements, and more targets, would place even greater strain on weapons stockpiles. There's also the question of saturation. A modern adversary like China or Russia doesn't rely on a single warship. They operate in layered formations: frigates, destroyers, corvettes, submarines, and carrier groups supported by shore-based radar and missile batteries. Engaging an entire fleet with expensive dedicated missiles is not just financially punishing, it may simply be insufficient if the enemy can absorb the losses. American defense planners recognized this problem and asked a different question. Instead of building more expensive missiles, could they transform weapons already in the stockpile, weapons proven, reliable, and produced in enormous quantities, into precision maritime strike tools? The answer was Quick Sync. What Quick Sync actually is and how it works. Quick Sync is not a missile. It is a guidance and targeting kit, an add-on system that converts existing Joint Direct Attack munitions, universally known as JDAMs, into precision anti-ship weapons. To appreciate how remarkable this is, it helps to understand what a JDAM already is. The JDAM program, initiated in the 1990s, took conventional unguided bombs, the kind dropped in World War II and Vietnam, and fitted them with a tail kit containing an inertial navigation system and GPS guidance. The transformation was dramatic. An unguided bomb, which might land anywhere within hundreds of feet of its aim point, suddenly became capable of striking within a few meters of a fixed target under almost any weather conditions. JDAMs were used extensively in Operation Allied Force over Kosovo, in Afghanistan starting in 2001, and throughout the Iraq War. They became the backbone of American precision strike capability, produced in the hundreds of thousands. JDAMs, however, have a critical limitation for naval warfare. They are designed to hit stationary targets. A ship is not stationary. A destroyer traveling at 30 knots covers roughly 600 meters per minute. By the time a JDAM fell from altitude and crossed the distance to a moving vessel, the ship could have moved several hundred meters from its GPS-designated position. Without the ability to track and lead a moving target, the weapon would miss. Quick Sync solves this with an advanced dual-mode seeker mounted in the nose of the weapon, transforming a GPS-guided bomb into an active hunter. Here is how the engagement sequence unfolds. After the B-2 releases the weapon at altitude, Quick Sync initially behaves like a standard JDAM, using GPS guidance to navigate toward the general vicinity of the target. This phase can cover many miles, with the weapon gliding toward the target area largely autonomously. But approximately 40 nautical miles from the intended target, roughly the final leg of its journey, a sophisticated seeker system activates and takes full control. That seeker combines two complementary technologies. The first is millimeter wave radar, operating in the 94 GHz frequency band. This type of radar is capable of generating detailed images of objects through fog, rain, smoke, and complete darkness. It does not care about weather conditions or visibility. The second element is an imaging infrared camera, which detects heat signatures and provides visual quality targeting data. These two sensors work together in a process called sensor fusion, each compensating for the other's limitations and together creating a targeting picture of remarkable clarity. But QuickSync does something that few previous weapons have attempted at this scale. It doesn't just detect a ship, it identifies it. The weapon's onboard computer carries a database of vessel signatures, cross-referencing the radar and infrared returns against known ship profiles to determine the type and size of the vessel. This matters enormously for what comes next. Once QuickSync identifies its target, it calculates the optimal impact point. Rather than simply aiming for the geometric center of the ship, the weapon selects a strike location just below the waterline, the area where flooding will be most catastrophic and most difficult to control. A hit above the waterline may cause serious damage. A hit below it, in the right location, can send even a large warship to the bottom. QuickSync is programmed to know the difference and to choose accordingly. The weapon is currently fielded in two variants. The 2,000-pound version carries a warhead powerful enough to critically damage or sink major warships including frigates, destroyers, and cruisers. The 500-pound variant is optimized for smaller vessels, patrol boats, corvettes, fast attack craft, and amphibious ships. A single B-2 Spirit can carry up to 80 of the smaller weapons or 20 of the larger ones in its internal weapons base. That means one stealth aircraft, undetectable on radar, could theoretically engage an entire naval task force in a single sortie. The cost per unit is approximately $30,000, a fraction of any dedicated anti-ship missile currently in service anywhere in the world. The Norwegian Sea test. The September 3rd demonstration was the culmination of a development program that began in 2022 with initial drop tests and progressed through increasingly complex scenarios over 3 years. But the Norwegian Sea test was different in character from everything that came before. This was not a controlled laboratory environment. This was a deliberate, strategically timed demonstration conducted in full view of adversary intelligence assets. The B-2 Spirit departed Whiteman Air Force Base in Missouri, the sole operating base for the B-2 fleet, and flew approximately 6,000 miles to the Norwegian Sea. The aircraft carried both variants of the QuickSync system. The mission was coordinated with Norwegian allies, and the joint nature of the operation was itself part of the message. 4 Norwegian F-35A Lightning II fighters provided escort and tactical coordination. AP-8A Poseidon maritime patrol aircraft, the same platform the U.S. Navy uses to hunt submarines, contributed maritime surveillance and targeting support. Norwegian submarines were positioned beneath the test area to capture footage of the strike from below the surface. The target ship was a decommissioned vessel positioned in the waters off Andøya Island, in conditions representative of real operational environments: rough Arctic seas, limited visibility, cold temperatures. The QuickSync weapon struck exactly where it was intended to, just below the waterline. The decommissioned vessel was completely destroyed. Russian naval and air assets were operating in the adjacent Barents Sea at the time, monitoring NATO exercises. Intelligence analysts assessed that Russian forces had direct observation of the test, or at minimum, gathered detailed signals intelligence from it. This was almost certainly the first time Russian forces observed QuickSync in action under live conditions. The psychological dimension of that fact is difficult to overstate. Why Russia should be worried. Russia's Northern Fleet, headquartered on the Kola Peninsula near the city of Murmansk, represents the most powerful and strategically important element of Russian naval power. It is home to the bulk of Russia's nuclear-armed ballistic missile submarines, the backbone of Russia's nuclear deterrent, as well as a significant surface fleet that includes the Admiral Gorshkov-class frigates, modernized Kirov-class nuclear-powered battle cruisers, and the carrier Admiral Kuznetsov. Russian naval doctrine in the Arctic and North Atlantic is built around a concept called bastion defense. The theory holds that Russian submarines, surface vessels, and land-based weapons create overlapping defensive zones, bastions around around key territory and sea lanes, making it too costly for NATO forces to penetrate. The Kola Peninsula bastion is particularly critical because it protects the sea lanes through which Russian ballistic missile submarines must pass to reach their patrol areas under the Arctic ice cap. Threatening this bastion has been a central challenge for NATO planners for decades. Quicksink complicates bastion defense in a fundamental way. The B-2's radar-absorbent coating and carefully designed shape give it a radar cross-section roughly equivalent to a bumblebee. Despite its 172-foot wingspan, Russian surface search radars cannot reliably detect it at operational range. That means a B-2 carrying quicksink weapons can approach the outer edges of a bastion zone without triggering the defensive response the bastion is designed to generate. By the time weapons are in the air, there may be no time to respond. Russian naval air defenses are designed primarily against missiles. Their Pantsir-M and Redut systems are optimized to detect and engage small, fast-moving targets flying low over the water. A precision-guided bomb falling from altitude presents a very different engagement problem. The geometry is different, the radar signature is different, and the engagement timeline is different. Existing Russian ship-based air defenses were largely not designed with this threat in mind. The Russian Zircon hypersonic anti-ship missile, which entered operational service around 2023, is undeniably impressive, capable of flying at speeds exceeding Mach 8 and striking targets at ranges of over 500 miles. But it costs tens of millions of dollars per shot, requires significant infrastructure to maintain, and can only be fired from specific vessels. Quicksink can be dropped from virtually any aircraft in the American inventory capable of carrying JDAMs. The asymmetry in cost and flexibility is stark. Why China should be worried? China's People's Liberation Army Navy has grown with breathtaking speed. In 2000, it operated a largely obsolete coastal defense fleet. Today, with over 340 vessels, it is numerically the largest navy in the world. China commissions new destroyers, frigates, and amphibious ships at a pace that has stunned Western analysts. Its Type 055 Rainier-class destroyers, at nearly 13,000 tons displacement, are among the most capable surface combatants on Earth. The Shandong and Liaoning aircraft carriers, supported by the newly commissioned Type 003 Fujian, China's first catapult-equipped carrier, represent a genuine power projection capability that would have seemed fantastical a generation ago. Underpinning this naval expansion is an elaborate system of anti-access and area denial, known as A2/AD. The DF-21D ballistic missile, developed specifically to target aircraft carriers at ranges up to 1,500 kilometers, was the first weapon of its kind and prompted significant concern within the U.S. Navy. Its successor, the DF-26, extends that range to over 4,000 kilometers, theoretically placing American carriers operating near Guam at risk. Integrated with shore-based radar networks, surveillance satellites, and over-the-horizon radar systems, China's A2/AD architecture was designed to deny American forces the ability to operate freely in the Western Pacific. Quicksink changes the calculus of this confrontation in ways that Chinese planners are only now beginning to grapple with. The B-2's operational range, with aerial refueling, is effectively unlimited. It has successfully flown non-stop missions from Whiteman Air Force Base in Missouri to targets in Afghanistan and back, a round trip of roughly 44 hours. B-2s based at Andersen Air Force Base in Guam are already within striking range of the South China Sea. B-2s operating from Whiteman could reach the Taiwan Strait with appropriate tanker support. China's A2/AD system is optimized to defend against ships and missiles approaching from outside the first island chain. It was not designed to defend against bombs falling from a stealth aircraft that cannot be detected until it is too late. The DF-21D carrier killer threatens an American carrier battle group. Quicksink threatens the destroyers and frigates that would be escorting the Chinese carriers. The logic of area denial works in both directions. For a potential Taiwan contingency, the scenario that most occupies the attention of planners on all sides, Quiksink's implications are significant. Any Chinese naval operation to blockade or assault Taiwan would require substantial surface forces operating in the Taiwan Strait and surrounding waters. Those forces would be visible on satellite imagery, detectable on maritime patrol aircraft radar, and trackable by underwater sensors. Quicksink would give American commanders a cost-effective option to degrade those forces from aircraft operating well outside the range of Chinese defensive systems. The economics of innovation underscore why $30,000 matters. The financial dimension of QuickSync is as strategically important as the technical one. Military procurement in the modern era is constrained by budgets, industrial capacity, and the fundamental tension between depth and sophistication. The United States Navy operates some of the most capable warships ever built, but it operates relatively few of them compared to the scale of the threat environment it must address. A Arleigh Burke-class destroyer, the workhorse of the American surface fleet, costs approximately $2.2 billion per hull. A Virginia-class attack submarine runs about $3.4 billion. These are extraordinary machines, crewed by highly trained sailors, and they represent decades of institutional and industrial investment. They cannot be replaced quickly if lost. In a high-intensity conflict, their preservation is operationally and politically critical. Against this backdrop, the economics of QuickSync are not merely impressive, they are transformative. At $30,000 per weapon, a single B-2 carrying 80 of the smaller variant represents a $2.4 million load of anti-ship strike capacity. That same bomber, delivering that load in a single mission, could theoretically engage more than a dozen enemy vessels. The cost ratio compared to dedicated anti-ship missiles is roughly 100:1. The cost ratio compared to the enemy vessels being targeted is orders of magnitude greater. This matters because it reshapes the cost-exchange ratio that military strategists use to assess the sustainability of conflict. If an adversary must spend hundreds of millions of dollars building a frigate, and the United States can threaten that frigate with a $30,000 weapon, the adversary faces an impossible arithmetic problem. They cannot build ships faster than the United States can manufacture guidance kits. This is precisely the kind of asymmetric leverage that has defined successful American military strategy at its best, finding ways to impose costs on adversaries that they cannot afford to match. What Norway's participation means. The involvement of Norwegian forces in the September 3rd test was not incidental. It was deliberate, and it carried a message as clear as the weapon itself. Norway occupies one of the most strategically sensitive positions in the NATO alliance. It shares a border of nearly 200 kilometers with Russia, controls access to the Barents Sea, and hosts key infrastructure that NATO would depend on in any northern conflict. Norwegian F-35s regularly intercept Russian aircraft probing NATO airspace over the Norwegian Sea and the Barents Sea. Norwegian submarines and maritime patrol aircraft monitor Russian naval movements through the GI-UK Gap, the Greenland-Iceland-United Kingdom Gap, which is the primary passage for Russian submarines attempting to reach the Atlantic. Norway's participation in the QuickSync test demonstrated several things simultaneously. It showed that American stealth platforms can operate seamlessly alongside Allied conventional forces. It demonstrated that the intelligence, surveillance, and targeting networks necessary to support QuickSync operations can be shared across national boundaries in real time. And it showed Russia that any conflict in the High North would not be a bilateral confrontation between Russia and America, it would be a fight against an integrated alliance with deep institutional ties and interoperating capabilities. This is something Russia cannot replicate. Russia's relationships with Iran and North Korea, while useful for certain transactional purposes, do not approach the kind of deep military integration that decades of NATO joint training have produced. China's relationships with Russia itself, and with a handful of smaller partners, similarly lack the doctrine, communications infrastructure, and mutual trust necessary for true combined arms operations at this level. The alliance advantage is not a soft diplomatic talking point. It is a hard military capability multiplier, and the Norwegian Sea test made it visible. An old platform made new. It is worth pausing to appreciate what the B-2 Spirit itself represents, and why its continued relevance is remarkable. The B-2 was designed in the late 1970s and early 1980s, during the Cold War, to penetrate Soviet air defenses and deliver nuclear weapons deep into Soviet territory. Its development was one of the most expensive and technically challenging programs in aviation history. The flying wing design with no vertical tail surfaces and a carefully sculpted shape minimizes the aircraft's radar cross-section to an extraordinary degree. Its radar-absorbent materials, maintained with painstaking care by ground crews, further reduce detectability. At a cost of approximately $2.1 billion per aircraft, only 21 were built, and 20 remain in the active fleet. For most of its service life, the B-2 was thought of primarily as a nuclear delivery vehicle, with a secondary conventional strike role against hardened targets, bunkers, command centers, underground facilities. Its contribution to naval warfare was not a primary consideration when it was designed. QuickSync changes that calculus entirely. The B-2's ability to penetrate sophisticated air defenses undetected. The capability it was built to provide turns out to be exactly what maritime strike operations require. A conventional anti-ship missile, however sophisticated, must survive the enemy's defensive systems to reach its target. A bomb released by a B-2 operating above radar detection range faces no such gauntlet. By the time the weapon is visible on any sensor, it is already seconds from impact. The B-2 was designed in the 1980s, flew its first test in 1989, and entered service in 1997. In 2025, equipped with weapons developed in the 2020s and operating alongside fifth-generation Allied fighters, it demonstrated a naval strike capability that did not exist in anyone's doctrinal playbook when the aircraft was conceived. This is a testament to the design philosophy of building platforms with the flexibility to evolve, a philosophy that the B-2 successor, the B-21 Raider, is designed to carry forward even further. The B-21 Raider, the Northrop Grumman B-21 Raider, which conducted its first flight in November 2023 and is currently in the advanced stages of developmental testing, will eventually replace the B-2 as America's primary stealth bomber. It is designed from the outset to incorporate the lessons of decades of B-2 operations, including lessons that programs like QuickSync are still generating. The B-21 is expected to be significantly cheaper to operate than the B-2, with a smaller crew, more modern avionics, and a design philosophy built around open architecture that allows new weapons and sensors to be integrated without the costly and time-consuming modifications that legacy platforms require. Where the B-2 needed extensive modifications to carry and employ QuickSync, the B-21 is expected to be ready for next-generation anti-ship weapons from the beginning of its service life. The Air Force plans to procure at least 100 B-21s, potentially more, compared to the fleet of just 20 B-2s. That scale matters enormously. A larger stealth bomber fleet multiplies the maritime strike capacity that QuickSync represents. If a single B-2 carrying QuickSync can threaten an enemy naval task force, a squadron of B-21s distributed across multiple bases in the Pacific creates a layered, persistent maritime strike threat that no adversary could reasonably hope to neutralize. The broader innovation philosophy. QuickSync did not emerge from a blank sheet of paper. It emerged from a careful analysis of existing capabilities, existing problems, and the gap between them. The Air Force Research Laboratory, the organization responsible for translating scientific advances into military applications, asked a deceptively simple question: what do we already have, and how can we make it do more? JDAMs were already in the stockpile in enormous quantities. The guidance technology was proven. The manufacturing base was established. The integration with existing aircraft was complete. The only missing element was the ability to find and track a moving ship. Adding that element, the dual-mode seeker with millimeter-wave radar and imaging infrared, was the innovation, not the entire weapon. This philosophy of enhancing existing systems rather than always developing entirely new ones has a distinguished history in American military development. The Joint Standoff Weapon, or JSOW, took existing warheads and added air glide capability and GPS guidance. The small-diameter bomb took the concept of precision and miniaturized it, allowing a single aircraft to carry far more weapons than before. The AGM-179 JAGM Joint Air-to-Ground Missile combined the seekers of multiple legacy missiles into a single, versatile package. QuickSync follows this lineage, and its success validates the philosophy for a new generation of developers. The lesson is not simply add a seeker to a JDAM. The lesson is that the most constrained resource in modern military development is not money or industrial capacity, it is time. A weapon developed from existing components can be fielded in years rather than decades. QuickSync went from first test in 2022 to operational demonstration in 2025, 3 years. A purpose-built anti-ship missile developed from scratch typically requires 15 to 20 years from concept to operational capability. The evolution of maritime strike. The September test was a demonstration of current capability, but the engineers and planners who built QuickSync are already working on what comes after it. Longer-range seeker variants, capable of acquiring targets at distances beyond 40 nautical miles, would allow weapons to be released from even greater standoff distances, further reducing risk to the aircraft and its crew. Enhanced seeker algorithms, incorporating machine learning techniques, could improve the system's ability to identify and discriminate between vessel types, distinguishing a hospital ship from a destroyer, or identifying a submarine tender that indicates a submarine operating area. Integration with additional aircraft platforms is ongoing. The B-1B Lancer, America's supersonic heavy bomber, can carry significantly larger payloads than the B-2 and has already been modified for maritime patrol missions under the Maritime Strike B-1 program. The B-52H Stratofortress, despite its age, has been fitted with modern avionics and is capable of carrying large external loads. Fighter aircraft like the F-15E Strike Eagle and F/A-18E/F Super Hornet, which routinely carry JDAMs, could potentially carry smaller quick-sink variants against lighter naval targets. As Allied interest in the system grows, Norwegian participation in the test is already generating discussions about technology sharing within the alliance. Quick-sink capabilities may eventually be integrated into the maritime strike arsenals of other NATO members, creating a distributed, alliance-wide anti-ship capacity that would be nearly impossible for any adversary to comprehensively address. The meaning of September 3, 2025. History does not always announce itself clearly in the moment. Occasionally it does. The Trinity nuclear test in July 1945 was immediately understood to have changed everything. The launch of Sputnik in October 1957 was recognized within hours as a turning point. Most military developments, however, accumulate significance slowly, their importance understood only in retrospect. The quick-sink demonstration in the Norwegian Sea may prove to be one of those moments recognized immediately for what it is, not because of the particular ship it sank, but because of what it revealed about the direction of American military thinking and capability. For decades, the dominant narrative in great power military competition has focused on the growth of Chinese and Russian conventional forces, their expanding fleets, their hypersonic missiles, their anti-satellite weapons, their electronic warfare capabilities. The implicit anxiety has been that America's lead, once so commanding as to be essentially unchallenged, was eroding. That closing the gap was only a matter of time and investment. What the Norwegian Sea test suggested, to anyone watching carefully, is that the race is not simply about the size of the fleet or the range of the missile. It is about the quality of thought applied to military problems, the ability to see existing capabilities in new ways, to ask different questions, to find leverage where adversaries see only constraints. A $30,000 guidance kit that turns a standard bomb into a ship-killing precision weapon, delivered by an aircraft that cannot be detected until it is too late, is not a marginal improvement on existing capability. It is a different kind of thinking about the problem entirely, and that, perhaps more than any specific technical parameter, is what will keep American military power relevant, adaptive, and formidable in the decades ahead.